Hi everyone. So I wanted to make a quick video about Laplace transform and transfer functions, since it's something that quite a few people have said still a bit confusing. So when we talk about the Laplace transform, we could ask one of two questions. We could either ask what is it, or we could ask how do we use it. So if we want to say what is it, well, we've got the definition up here. You take a time domain signal, so this might be a force or a position or a velocity as a function of time, and then you just compute the integral over an infinite time interval of that signal times e to the minus st, and that's the Laplace transform as a function of s. But that's perhaps not that helpful because at least most people, at least when they first see this, it's pretty hard to see what's actually going on and why anybody would ever want to do that. So the real way we come to understand Laplace transform is by using it. And so how is it used? Well, it's used as, you could think of it like a change of variables. So sometimes when you're computing, say, an integral, changing from Cartesian coordinates to polar coordinates might make things much simpler. Say if there's some object which is rotationally symmetric. It's similar in this case. There are some things that changing from the time domain to the s domain, or the frequency domain, makes certain things much easier, in particular dealing with linear differential equations. And that's going to be one of the main topics of study in AMME 3500. So the nice thing is, although the Laplace transform is defined by this pretty ugly looking integral, we almost never actually deal with this integral. Part of the reason is that your ancestors have computed these nice tables of Laplace transforms. So for a lot of the kind of standard signals that we're dealing with in system analysis, people have already worked out what the Laplace transform is. And there are ways of combining those and expanding those and so on. So the main way that we are going to be using Laplace transform is to analyze ordinary differential equations. So we might say, have an ordinary differential equation like, say, second derivative of y plus 3 times first derivative of y plus 7 times y equals, say, u dot plus 2u. So here u is some forcing function and y is the output that we want to study. And these are just numbers I kind of picked out of the air. So what good does the Laplace transform do? Well, what it does is it converts a differential equation into an algebraic equation. And there's a key property of the Laplace transform, and actually you see this in the table. So we've got the differentiation theorem and also higher order derivatives. And the main differentiation theorem states that if we've got a signal f of t and we want to deal with its derivative, so we want to say what's the Laplace transform of df dt, that's going to be s times the Laplace transform of f. So if we've already got the Laplace transform of f, then that's useful, minus the initial conditions of f. So this shows up in your tables here as item number 7. Now, very often we're going to be dealing with systems responding to forcing function inputs, and we're going to ignore initial conditions or set initial conditions to 0. And so in that case, this disappears, and we get the really nice property that differentiating a time domain signal just corresponds to multiplying its Laplace transform by s. And we can keep going here to higher derivatives. We can have a look at the table for the second derivative. If we had both of the initial conditions equal to 0 here, these would disappear, and we just get s squared times f of s. So let's look back at our differential equation here, and we can say, if we're assuming initial conditions are 0, so let's say y dot of 0, and y of 0, and u of 0 are all 0, then we use our differentiation theorem and we say replace y double dot with s squared times y of s plus 3 times s times y of s plus 7 times y of s, and then we do the same on the right hand side, equals s times u of s plus 2 u of s. And then we can group our y and our u terms together, so we can write y of s times s squared plus 3s plus 7 equals u of s times s plus 2. So we started in the time domain with a differential equation, so something that relates derivatives of y to derivatives of u, and we ended up with something in the s domain which is just an algebraic equation. It says y and u are related just by some polynomials in s. And then we can say, well, let's actually just divide y by s. So let's see, y of s over u of s equals s plus 2 over s squared plus 3s plus 7. And this is a really important object. This is something we call the transfer function. And often we're going to use symbols like g of s for that, or it might be c of s or h of s. G of s is often used for the system dynamics, k of s for a controller. So the transfer function tells us that if I've got some input in the Laplace domain u of s, and I want to know what the output is, I just multiply it by g of s. And g of s is this rational function. So how do we use that for system analysis? Now we can actually make use of some of the things we saw in the lecture this week. For example, the rules about block diagram reduction for feedback transformations to see how this is useful. So I'm going to illustrate this with an even simpler example than the one on the previous page. So let's say we had a differential equation y dot minus y equals u. Now if I want to compute the transfer function for that, I say, well, this is going to be in the Laplace domain s times y of s minus y of s equals u of s. Again, assuming initial conditions of y is 0, so that this is the differentiation rule. And then that gives me the transfer function g of s equals y of s over u of s equals 1 over s minus 1. And we would often draw that in terms of a block diagram as the forcing function coming in from the left. Inside the block, we write the transfer function. So it's going to be 1 over s minus 1. And then the output on the other side. Okay, so now what? How do I say how this system is going to respond to particular types of inputs? Well, I might just say, look at my table of inputs. Maybe I want to see how it responds to an impulse. If the input is an impulse, then the Laplace transform of that input is just 1. So that's really easy. We can go back here and we say, well, if u of s equals 1, then y of s equals g of s times u of s, by definition of g of s, and that equals just 1 over s minus 1, because that's what g of s is. And then I would look back at my Laplace transform tables and see, can I go backwards? So I'd look down on my Laplace transform side and say, do any of these look familiar? And well, 1 over s plus a looks right, but a is going to be equal to minus 1 here. So we've got, this is 1 over s plus a with a equals minus 1. Right? And so we've got e to the minus at times u of t. Now don't be confused by this u of t. This is a convention that the book uses just for the step function. So it's something which is 0 before t equals 0 and 1 afterwards. we're not going to use that because in our course we're going to assume basically that time starts at 0, so we don't have to worry about what is happening before t equals 0. So this u of t function would always be 1. Okay, so it just disappears. So just ignore that on all of these. So it's just going to be e to the minus at, but a equals minus 1. So our actual time domain signal here is going to be e to the minus 1, which is e to the t. And that's not so good from a control system's perspective. That's something which goes up exponentially. And usually something going up exponentially is bad. It means that something is going to blow up eventually. Pressures or velocities or something like that are getting too high. Okay, so what happens if we put this in a feedback loop? So one of the kind of standard feedback loops that we've been seeing in lectures is you've got some reference signal coming in from the left, and then this goes into a summing junction, and this is going to be a minus sign here. And here we've got a control gain, so I'm going to call this K, and this goes into, this is going to be the control signal here, U of S. This is our system here, 1 over S minus 1, so that's G of S. This is our output, and then the output gets fed back to, and we look at the reference minus the output. So the reference would be some desired level for the output, and then the reference minus the actual output is the error signal. So this is E of S. Okay, so now if we've constructed this feedback loop, so what's happening practically? We've got some reference signal that we want the system to be at, what we want the output to be at. We measure the actual output, we subtract the actual output from the measured output, that gives us our error. We multiply the error by some number k, or later on we'll see this could even be a dynamic system as well. That tells us how to set the control signal, and then that goes into the system itself. So we've got this feedback loop happening at all times. And you remember for block diagram reduction for systems of this form, we have the rule that the overall transfer function, so we're looking for y over r now, is going to be the forward path over 1 plus the complete path, right? So the forward path is anything here, if you look from r to y, and you just trace all the arrows until you first hit y, without going through the feedback loop, that's the forward path. And then if you look what happens in the feedback loop, that's the complete loop path, right? So that's the forward path times the reverse path. And so here we've got the forward path, which is k over s minus 1 over 1 plus the forward path times the reverse path. In this case, the reverse path is just 1. So again, it's the same, 1 over k over s minus 1. We've also used here the fact that if you've got a composition of k and s minus 1, the transfer function of that is just k over s minus 1. We just multiply the two transfer functions together. So now we can actually, let's multiply through by s minus 1, and we're going to get k over s minus 1 plus k. And now k is some constant, and we can set that to whatever we want. This is something that we control as control engineers. And it should be clear from looking at our tables here that if we want something that's going to be exponentially decaying, so we want a response that's going to go towards 0, so a stable response, then we're going to want a transfer function of the form 1 over s plus a positive number. So we want k here to be bigger than 1. So let's say k equals 2. If we have k equals 2, then we're going to have 2 over s minus 1 plus 2, which is s plus 1. So the block diagram reduction of this feedback loop here is going to be, let's draw that on a new page, r of s goes into 2 over s plus 1. And that produces y of s. Okay, so this is just a reduced form of this feedback loop with k equals 2. And then we're going to do the same thing that we did here to analyze the response to an impulsive input. Okay, so if we've got an impulse input on reference, and the reference is going to be equal to 1. And so y of s, let's call this t of s for the closed loop transfer function. That's a letter we sometimes use for that. Y of s equals t of s times r of s equals 2 over s plus 1. And then if we look at the inverse Laplace transform to get back to y of t, so we look at this inverse Laplace transform, again we've got something of this form, but now we've got a positive a here, and we've got a 2 there, so the 2 we just take out the front, and we've got e to the minus t. And so this is going to be a time response now, which starts at 2 and goes towards 0. Sorry, I didn't draw that so well, but that's something which converges exponentially to 0. So now we've actually, starting with an unstable system, this system here, this differential equation, with an impulsive input, the output shoots off to infinity. By putting it inside a feedback loop, we've actually stabilized it. So now we've got this stable system, and we can tell it's stable. One way to tell it's stable is by looking at the pole, so looking at the roots of the denominator here. Here this pole has a negative real part, whereas this pole has a positive real part. We could also go on and we could study the response of the same system to different inputs. So let's say if we wanted to look at the response to a step input, okay? So a step input, often we're going to see a step change in a reference input when you move from one set point to another. So an example might be cruise control for a car. You're cruising at 60k an hour, and then you go onto the freeway and you want to step up to 110k an hour. Then you're going to see a step change like this in the reference. So then the Laplace transform of a step change is 1 over s. So if we had a reference of 1 over s, then we're going to have y of s equals 2 over s plus 1 times 1 over s, okay? Or we can write that as 2 over s squared plus s. And then how would we actually compute what the time response here is? Well, we do the partial fraction expansion of this. And now the key point in the partial fraction expansion is actually, it's easier in this factored form. So we're going to have y of s equals a over s plus 1 plus b over s. And then the for some constants a and b, which you can go through and compute. And then the time response is going to be, we look at the inverse Laplace transform of these two components. So you've got 1 over s plus a and 1 over s. So it's going to be a times e to the minus t plus b. 1 over s, the inverse Laplace transform is just, well, after t equals 0, it's just 1. So for t greater than or equal to 0, this is what the response is going to look like. Okay, so it's going to be some constant and some decaying exponential. So it might be something, typically it might be something like there's going to be some constant that it converges to when this part goes to 0. And if we're starting from 0 initial conditions, it's going to look something like this. Now, for the purposes of control design and stability analysis, often I don't actually particularly mind what these terms A and B are. What I care about is what the poles of the system are. So I care about the fact that this has this denominator has a root which has a negative real part, and this overall time response has a constant part plus a decaying exponential part, so we're not going to get any of this unstable behavior. So that's a quick example of how, basically, what have we done here? We've used the fact that the Laplace transform allows us to convert differential equations into algebraic equations, and in particular gives us transfer functions. So transfer functions are the ratio of the Laplace transform of the output and the input, and that's going to be written as a ratio of polynomials. So transfer functions for linear time invariant systems are always ratios of polynomials. A nice thing is that the Laplace transforms of a lot of the kind of basic building block signals that we're working with are also ratios of polynomials. So when you go through and you compute, let's say, an output which equals a transfer function times an input, you're going to still end up with ratios of polynomials. And then we can look at a few different cases, but then if you have higher order ratios of polynomials, you might do partial fraction expansion to see what happens. So we've seen how converting a differential equation into an algebraic equation can help us understand the input-output response of a system. We've also seen a very simple example of how putting a system inside a feedback loop, so measuring the output, computing the error from where you want it to be, and then multiplying that by a constant and putting that around can actually stabilize an unstable system. What we're going to look at in the next lecture is going to be really, questions like, does it actually end up at the right value? So does the output actually converge to the reference value, or does the error go to 0? But I won't discuss that at the moment. So hopefully that's cleared up a little bit, at least the way that we use Laplace transforms. What you'll see is that throughout all of this, I never actually even looked at this integral. I never tried to compute any integrals like this by hand, and that's typically the way things work. When we're dealing with Laplace transforms and transfer functions, we're never actually really dealing with this integral. We're just dealing with manipulations, products, and so on of polynomials and rational functions. So hopefully that's cleared that up a little bit. Again, post any questions to Ed if anything in this was unclear.